I would have a question, but the question is for Karl Mangieri, who is not here, if I'm correct, but maybe the question could be answered by others. I see Jan-Hendrik Evertje is among the audience, and maybe...
Oh, yeah, sure, yes.
Yeah, you are here, Jan-Hendrik?
Yes.
Oh, that's nice. Hello.
Oh.
It's very good that you participate. So my question is, Kalman yesterday pointed out the result of, I think, Koymans concerning a Catalan equation for finitely generated domains.
Yes.
What is the method used by Koymans?
Well, it's more or less the method was more or less pointed out by Kalman. First, you have to do it over number fields.
Okay, so it's in fact the so to say the general method Kalman pointed out.
Yeah, it's basically over number fields an extension of the Rot-Tiedeman's method. So linear forms and logarithms, both in the ordinary p-adic case, you have to do it over the s-integers. And then, well, yes, with the specialization method, which was mentioned by Kalman, you can extend it to finitely generated domains. So with specialization method, you can more or less map the equation over finitely generated domains to the Catalan equation over the s-integers. And then, okay, you have effective results. So you can compute effective bounds for the solutions over the s-integers. Hello?
Yeah. And the bounds are more or less completely explicit.
Well, you can make them explicit. There are some absolute constants which have not been computed.
Okay. So there's nothing special what has to be used for this equation?
Well, no, just linear forms and logarithms for over the algebraic, over the s-integers, over the number fields, and then with the specialization method, you can extend it to finitely generated domains.
Okay, yeah, thank you. I thought there is something special which has to be used at this place. Okay. Yeah, are there other questions? No. Additions to lectures. Problems. No. Joel, do you like to say something?
Yes, even maybe a suggestion, because I think this is not the last conference in this form of virtual conference, so whatever can be discussed about it, if you have some suggestions, it's also useful.
Yeah, that's a good question. General suggestions for how to do such a conference, how to proceed. Do you have ideas? Because we were in a hurry, we had to fix everything within a very short period. So maybe there are general suggestions. No general suggestions. Oh, Nikolai is typing. Now people are typing. I am almost happy. Yes, Mark, you can share with picture. I asked Guillaume how to do. I can try to do it myself, but I have to find Mark Munch. Maybe he's sitting very close to.
I just took a picture of some very easy problem, but it's easier if I show what I wrote.
Yeah.
I don't know in this big blue button where I can do it.
Wait, you have to. Do you have a camera?
Yes, but might be not clear if I just show you. Can I share my screen in some way?
Robert, I think you can put him.
I can make him to the moderator.
No, you can make him presenter.
No, I say make him to the moderator, and I do that now.
Okay.
Mark,
he is presenter. Mark is presenter.
I have some tools now. Okay, let me see.
Okay, great.
Tools.
Aha, now okay. Thank you, Guillaume. Thank you, Guillaume.
I don't know where is this. Plus, maybe.
You have to push on the button on the right.
Where is
the bottom of the screen? At the right, just near the webcam button.
And where can I do here?
When you click,
I have annotation, something like. I cannot share something. Or at least
non, Marc, normalement, tu peux partager ton écran en cliquant sur le bouton à droite en bas.
Oh, I have it now. So wait. Okay. I will try to. Sorry, it takes a bit of time. Should open this.
I think in the meantime, Nikolai wants to say something.
Yes, okay, please, Nikolai.
Okay, so yes. When I was when I was trying to say something for the first time, it turned out that I lose the connection. So I want to say, as for some general suggestions, I want to say that maybe it is reasonable to have some kind of rooms for conversation in very small groups.
Yes, Nikolai, that is possible. This is possible within this system, but we didn't try it because of maybe complications, but that's definitely possible.
Yes. Okay.
And if you like to do this in the next few days, we can try to install it.
I think we should try different opportunities. So let's try. So
okay,
maybe...
I will discuss it by email with Celine. Yes, so we had this idea also in Marseille. Yes.
Okay, and also I want to formulate a problem, but it is rather a problem for students, but I'm not sure. My students are not able to solve it. Also, I am not able to solve it myself, at least in a reasonable time. So maybe I write a problem. It seems to me that it sounds not very bad.
That's a good idea. So we have to fix. I think Mark. I can see. I see on the screen some written formula. Is that Mark or is that Nicola?
It's me, but is it readable?
Oh, wait a moment. Not very, very good, but I will try it.
I don't know, like
Somebody
it's a
should
picture.
Yes,
with
it's
focus.
readable, definitely.
One.
It's readable.
Yes.
So maybe I can start to discuss.
Yeah,
it.
please, Mark, start, and afterwards Nikolai poses his problem. Yes? Is that fine, Nikolai?
Yes, yes, for sure.
Good.
Yeah, it
So
makes
please.
it complicated online. But... Okay, so it's a very simple problem. So you take a polynomial with real coefficients of degree bigger than 3, and you want to count the solution, which is kind of energy. So you count Pn1 plus Pn2 minus Pn3 minus Pn4, very small, so smaller than 1. And you count all the solution when you take the first n values. So if you would have like some polynomial with integer coefficient, usually you will count like this thing to be 0, and it's like something not hard to do. But here you have real coefficient, and you want to bound this. So trivial, this thing is between n2 and n4. And I would like to know if you can get better bounds, like something, you should expect this to be like the diagonal plus a bit more. So something like n squared plus epsilon. But even if you can prove something like n to the 5/2, would be interested to see. So this has a connection with my recent work with Christoph Eisleitner and Daniel Elbaz about percorrelation of real sequences, where this is one of example is to take polynomial sequences with real coefficients.
Okay. Yes, thank you. Are there comments to that problem?
So maybe I add one comment. If you take your polynomial to be in Z, you can easily prove it's n squared plus epsilon. And we can also prove it for degree equals 2.
Yes. Are there other comments? So now I have problems to remove my full
I will
screen.
stop sharing if it's okay.
Yes, please. Thank you very much. I see now there is Daniel Elbaz saying it's fine. Okay. Okay, there, Celine, thank you very much. She is answering the question of Nikolai to creation smaller rooms. We had the idea, the billiard room. So maybe we can make this available tomorrow for small group discussions. Yeah, to answer Philip Habecker's question, yes, this is also a good suggestion. We should keep the problems on some page somewhere. So my question to Guillaume is that, do you record the problems, the slides?
Yes, yes.
Okay, then we can make them available. Thank you, thank you. Okay, maybe there are few further comments before we start with Nikolai. Yeah, there are answers. Answering questions of Bruno Martin. Why is it easy? Here, this question, and this question already is answered by both of them, by Mark and by Daniel. Bruno, are you satisfied? Yes, he's satisfied. Joel, whom should Olivier Robert help?
Mark.
Ah, okay, good.
because
That's what I got. Yeah.
Because
Yeah.
actually this type of spacing
Okay,
problem,
so this is mathematics and data transmission.
just I could explain just
Yeah.
this type of spacing problem is very classical in exponential sum
Yeah.
problems, and I think Olivier Robert should know how to do that almost immediately.
Yeah.
Yeah, we actually use Olivier Robert results for n to the theta. So that's true. Like his paper about exponential sums.
Yes, but
which is
if you speak with him, maybe he also knows to answer the question not in the paper.
Yeah, right. We exchanged email already, but
okay.
So far, no solution. But
yeah, Gerald, wouldn't be technical to have a discussion, seeing everyone and by voice. Yeah, that should be possible to see the people presenting. I don't know how to fix it fast. Guillaume, is that possible that when we ask Nikolai to present his problem, that we can see him?
I can write on a screen if you give me. I can write.
Yes, but we want to see you.
Can you put your camera?
Okay, I will try.
Nikolai, you have to put your camera.
I'm here.
Yes, great.
Yes.
We
I'm
can
here.
see you.
Okay, so I think one moment. I should be. Okay. I will formulate a problem. It may be easy, but not very trivial, and I'm almost able to solve it. However, I think it has a nice formulation. So let's A and B, alpha, beta, be real, okay? Alpha, beta, be real. To prove that there exist infinitely many Q natural such that Q divides the sum of squares. This is square plus beta Q square. Here, sum of squares, and these brackets mean integer part. Do you see the problem? Is it clear? Is it clear?
Yeah, that's clear.
Is the formulation clear? I am almost able to do this. I am almost able to solve it, but what I'm explaining what I do mean by almost. Look, so we can have integer part, ordinary integer part, or upper integer part. Here we have two places, the first one and the second one. We can put in both places either both lower integer part or both upper integer part, or sometimes in one place lower integer part and another upper integer part. So we have three combinations. I can prove that at least for one combination there exists infinitely many Qs. It follows from something like Klein-Bock-Merrill theorem about approximations on intrinsic approximations on spheres. But for integer part itself, I don't know if it is true. So I believe that it is true, but I cannot prove. So it's a very, it's in my opinion, it is very nice formulation, and it is very pure, as it is a problem itself. I'm sure that it will not lead to progress in general mathematics. However, I think it could be nice.
Okay, yeah, that sounds a nice problem, definitely. Are there comments on that?
I will be happy to know the solution.
Yeah, there is a comment, a further question of Philip Habecker. Can you read it, Nikolai?
In my proof, it does depend. For alpha beta, there exists a combination. Yes, yes. In what I can prove, combination depends on alpha beta.
Okay. Further comments, questions to that?
Moreover, I do not believe in a proof in this fact when we have more than two squares, maybe five squares. I don't know for 3, but 5, 9, or for many squares, I think the answer is negative.
Further remarks to that problem? Okay, so Nikolai, thank you very much. Do you have another problem, or should we ask other people?
To start, so I was not the first, but I just wanted to start, as nobody wants to. So I think I will formulate just this problem now.
Okay, so thank you very much. So,
as for other ones, I need to speak. I think I should give opportunity to give a talk to somebody else.
Okay, so please ask questions, formulate problems, give hints to the organizers how to do it better. Okay. It seems at the moment no further questions. So Nikolai, you can formulate the second problem. Please.
So I have many problems.
Yeah. If you have many, you just have to apply the axiom of choice.
So if necessary, I can speak. I can formulate another problem.
Please.
Okay. So, but I'll try to clear the screen. Yeah. I can formulate two problems about Minkowski function. One function is question mark, another one is not question mark function.
Okay.
However, this problem is not very popular, but it is so. What is question mark function? We have Stern-Bracco sequences. So we have 0, 1, and 1, 1, and we can add numerator with denominator. So here will be 1/2, and so on and so on. It's Stern-Bracco sequences. And so here's 1/4, here's 2/3, and so on. So if Fn is Stern-Bracco sequence, then we can consider the distribution function. It means that we deal with the number of elements of Stern-Bracco sequence up to x divided by the complete number of elements Stern-Bracco sequence. And the distribution function is so-called Minkowski. Oh, this is here. I would like to limit when n goes to infinity. This is Minkowski question mark function. It is a strange function, which is monotone. Monotone function is differential almost everywhere by famous Lebesgue theorem. It has stable points, 3 trivial stable points, 0, 1, and 1/2. It is possible to prove that in rational points the derivative is 0. So if I look for other stable points, it is obvious from continuity that we have at least two stable points in the interval 0, 1/2 and 1/2, 1. The folklore conjecture, which was formulated, I think, only in my preprint, that these 2 points are just unique points. So we have just 3 rational points and just 2 more points, which are fixed points of Minkowski question mark function. I mean, the solutions of this equation. So this problem, I think, is not so popular. However, I would like to say that recently my students were able to prove that if we have the smallest point in this interval or the largest point in that interval, so stable point, so x0, then it is not very good approximable. So I mean that always happens q square and here log q. So however, if the main problem is to prove that there is no more stable point, no more stable points, but these 3 rational points and these 2 irrational points. However, we do not know if there are just 2 points. Maybe there are more points. By the way, that there exists just 2 points is obviously, this is a computer evidence. So the problem to study integer stable points of Minkowski function and to give a good bounds for irrationality measure. Probably these stable points are typical. I mean that partial quotients for them should be unbounded. So I think I said too much, and I think somebody else should continue.
Yeah. Thank you very much. Many thanks, Nikolai.